So we have been looking at convergence theorems, and now we will define several different types of convergence, starting with convergence in probability. And remember that this a lot of this is based on originally on the Chebyshev theorem, but we now define three convergence concepts which we actually want to use. So first of all, if we start with a sequence of random variables, we will say that it converges to X in probability if the probability that these two, the sequence and the target random variable, are close, converges to 1. In other words, this is just a regular numeric limit. The limit of this is 1 for any epsilon. And we then write Xn converges in probability to X. This has several important theorems which use this type of convergence. For example, if we have a sequence of random variable, all with the same mean, all with the same finite variance, then their average, the average being just the sum of the first n, the average converges to the expected value. And we would typically say in words, the sample mean converges to the population mean. And this is a trivial use of the Chebyshev inequality to prove this. Now, we often want to estimate unknown numbers, and this is an example of this. We had an example where we used the mean of the random sample, and we say this converges in probability to the true expected value. Now, what this means also is that if we collect a set of numbers and we think this is a reasonable model for how they were generated, then we know that this collection of random numbers will be close to the true mean, if you like, with high probability, if the sample size is large enough. Now, in that case, this is really an estimate, and the sample mean would be the corresponding random variable, which we would call an estimator. And we do this in general. An estimator is just an appropriate function of random variables. We usually think of the estimator in the context of a number or an unknown parameter to be estimated. And we say it is unbiased if the expected value is equal to theta for all n. Now, an estimator is correspondingly consistent for theta if it does tend towards theta in probability, if it converges to theta in probability. So notice we may have a biased estimator which is consistent, and we might potentially have an unbiased estimator which is not consistent. And there are several examples of this. One important theorem here is that if we have a continuous function, then a continuous function of a sequence of random variables converges to the corresponding function of the limiting random variable if the original series is convergent to that random variable. And we have a lot of corresponding theorems for the probability, for example, of getting heads in coin tosses, and so forth. Now, the next type of convergence will be the almost sure convergence. So that's if you have a collection of random variables and a target random variable, and if the probability that they actually have a limit equal to the random variable or closer than epsilon, if that's equal to 1 for any epsilon, then we talk about almost sure convergence. So what this means is that the limit of the random variables x is equal to, of xn is equal to x or within epsilon of x with probability 1 for any epsilon. And this is a much stronger definition. It's a stricter requirement. And we can look at this, what this means in terms of omegas on the original sample space. And we can look at them together. And we can then see exactly how this works. And you just need to read the details if you want to go further. There is a corresponding strong law of large numbers where you actually do not need the variance to be finite. You simply need IID random variables. If the mean is well defined, if it has an expected value, then the sample mean will converge to the population. And this convergence then is almost sure convergence. The final type of convergence, which we tend to use more in statistics, is convergence in distribution. And this is different from the other two, because it simply says that xn converges to xn distribution if the corresponding cumulative distribution functions converge. So in other words, if you have the cumulative distribution function of xn and the cumulative distribution function of x, then we just require that the cumulative distribution function for the xn converges to the cumulative distribution function of x at points x where f is continuous. So it doesn't need to converge everywhere. And this is it's actually quite common that there might be a finite or even countable set of points where f is discontinuous, and since f is continuous from the right, the fn sequence might converge to the wrong points where f has jumps, and that's fine. We still talk about convergence in distribution. So, and the reason for this is that we can then approximate probabilities for x based on probabilities for the xn. And we have a lot of examples, and again, I urge you to go through some of these examples. Now, probability in distribution is denoted with a little d. We usually use a script d, and we have these a whole suite of theorems. For example, the common approximation of a binomial probability using a Poisson is simply based on the basic result that a set of binomial random variables will converge to a corresponding Poisson random variable if the probabilities also go appropriately to 0. So basically what that means is that you can approximate probabilities of a binomial if you have a large n and a low Pn, then this would be a reasonable approximation. Now, there are two important theorems here in the end. First, if we have convergence in probability, then we have convergence in distribution. So in other words, convergence in distribution is weaker than convergence in probability. And secondly, if we have convergence in distribution to a constant, then we have convergence in probability to a constant. So if we can show convergence in distribution to a constant, then we also have the usually stronger type of convergence. So in other words, the two are equivalent by combining these two theorems. These two convergence types are equivalent if we're talking about convergence to a constant.